Okay, good evening, everyone, or good morning or good noon, depending on what time you are watching this video. And I would like again to apologize for earlier. No, we were not able to do the synchronous session, but I hope you had fun seeing your teachers again, and they were quite happy to see you guys as well. Okay, so let's begin with practice problem number one. So here, this is a fairly simple problem. You just need to convert the given stress block, this one, into an equivalent stress tensor. Okay, so remember that when we do a stress tensor, the stress tensor is a square matrix wherein the diagonals are made up of the normal stress values, which is the sigma x or sigma xx. Then we have sigma y, and then we have sigma z. Okay, then uh, for the other positions, it is comprised of the shear stress values. Okay, so for this one here, this is sigma or tau xy, which is the shear stress on the x plane moving in the y direction. And here, since the stress tensor is actually a symmetrical square matrix, then therefore these two are just equal, no? So this is sigma y, tau y x, which is the shear stress in the y plane moving in the x directions. And obviously you can interchange them, no? Because again, this is a symmetrical matrix, so they can interchange positions, no? Because again, they are also equal in value. Okay, then we have here, this is tau in the x plane moving in the z direction. And let me just complete this, no? We have tau in the y plane moving in the z. And here is tau of your z plane moving in the y direction. And lastly, we have tau z moving in the y. I'm sorry, this is supposed to be tau z tau in the z plane moving in the y direction. Okay, so let's just fill this out, no? So sigma x, this is just the normal stress moving in the x direction onto the x plane. No? So this is our x plane, and this is your and we have 5 megapascals. That is a compressive load now. And our convention is if we have a compressive load, it is given a negative values. Okay, that's -5. Then let's look at the y plane. So this is our y plane. And in our y plane, and this is actually the positive y plane. No? So this will, if you read your module, this is important, no, when we try to look at the positive or negative sign of our shear stresses. Okay, so this is the positive x plane, and obviously the opposite side, this side over here, will be the negative x plane. Okay, but we actually don't need to draw it now. So let me just remove it. So again, in the y plane, we have no normal stresses, therefore we have a 0 value here. Then in the z plane, this is the positive z plane, we have a tensile stress moving in the z direction now. So since it's a tensile stress, then we give it a positive value. Okay, so we completed the diagonal. Now we need to find the shear stresses now. So let's start with tau xy or tau yx, which again are equal values. So let's look at the x plane moving in the y direction, which is this value over here, which is also equal to this value over here. Okay, so this is 3 megapascals, and it's in the positive x plane moving in the positive y direction. Therefore, it should be given a positive value. Okay, so positive gives us a positive shear stress value. So that's +3. And we can also check it in the y plane. No, this is on the positive y plane. So again, these are equal values, no, because they are equal and opposite in direction, so that our stress block will be in equilibrium. Okay, so if you check it in this positive y plane, this is on top of the positive y plane, moving on the positive x direction. So positive x is this way. So this is all the positive value, positive and positive z value. So again, it's 3 now. Now let's look at, so this is the same value, no? Tau yx is just equal to tau xy. Okay, now let's look at the z direction on the x plane. So that's tau xz. So this is, let's look at this one. This is this is 6 megapascals. This one, 6 megapascals on the positive x plane, moving in the positive z direction again. So this is again positive. And again, we can also make the same analogy in the z plane. No? So this is the positive z plane, and it's moving in the positive x direction again. So that's why it's a positive value. So again, just to refresh your memory, if it's the positive plane and positive direction, then we have a positive sign for the shear stress. If it's a positive plane, let me just increase my working area now. If we have a positive plane but a negative direction, then we get a negative shear stress. If it's a negative plane and it's a positive direction, then we have a negative shear stress. And lastly, if it's a negative plane and it's moving in a negative direction, then you'll have a positive shear stress. Okay, so let's look at the last shear stress value, and let me just fill this out now, because again, tau xz is just equal to tau zx. I'm sorry, this is supposed to be tau zx now. Tau zx. Okay, so in this case, this is your let's look at the 2 megapascal shear stress here. No, it's on the positive z plane, but it's moving in the negative y direction. Okay, because the positive y is going upwards. So this is a negative y direction. Therefore, it's a positive plane moving in the negative direction. We have a negative shear stress. So this is -2, and it's just equal to negative yz. And also, again, we can make the same analysis here, no? So this is on the positive y plane, and it's moving on the negative z direction. So this one, positive y plane, and moving in the negative z direction. Okay, so that's practice problem number 1. Okay, we proceed with practice problem number 2. And we are given this stress block, no? And in this given stress state, we are to determine the principal stresses, the orientation of the principal stresses, as well as the maximum shear stress, the shear state, the stress state at 30 degrees clockwise from the x plane, and in all of this, we want to plot and label all the relevant answers now. Okay, so obviously this is a stress state that is along 2 axes. Therefore, we have a 2D stress state now. So when we have a 2D stress state, it's always easier to use more circle now. Okay, so let's draw more circle here. So we have the sigma axis, and we have the tau axis. And this is arbitrary, no? Which we give a positive value, but I'll just do a counterclockwise is positive for me. Okay, it wouldn't really matter, no. It wouldn't change your answer. So we have a tensile again, like the previous example. If it's a tensile stress, then we give it a positive value for tensile, and for compressive, we give it a negative value. Okay, so let's look at the problem. We have a positive 230 on the y plane, so that's 230, and I'll just do an estimate class now. So this is, if this 100, 200, and 230 somewhere here. So that's 230, and the shear stress is counterclockwise, 480 megapascals moving counterclockwise. So that becomes, let's do 1, 2, 3, 4. Let me just rescale now so that it will fit. Okay, let me just do this all over again, no? Because hindi kasya yung ginawa ko. So I'll just move this one. I'll move this. Tapos increase ko na lang yung scale ko na. Okay, again, I'm using tau or counterclockwise. The counterclockwise direction is the positive direction. Okay, so again, I'll do 1, 2, and this is around 230, and let me do 1, 2, 3, 4, 80 somewhere here. So we have 230 and 480. This is 230, 480. Now let's do the other direction. This is also a positive value, no? So that's positive 350. So if this is 300, then 350 is somewhere here now. This 400. So 350, and this is 480 moving in the clockwise direction. Therefore, it's a negative value now. So I'll move by the same amount. So that's 1, and it's okay if it's not that accurate dito class now, because eventually we will just use calculators so that we can get an accurate answer. Okay, so we have 1, 2, 3, 4, 80 is somewhere here. So I'll move it. It's somewhere here now. So this is 350, and we have 480. Okay, so if we connect this line, we will find the intersection between, we can find this point, no, the center point. So the center point is just equal to, we can compute this manually, no? So we have 230. The center point is just equal to 230 plus 350 divided by 2, since it's half the distance between these two these two normal stress values, no? So we should get, let me just pull out my calculator class now. Divided by 2, we have 290. Okay, so this is 290. So our center point is 290 and 290. Okay, so we have a radius of, we can actually compute the radius, no? If it's, our radius is equal to, we can do this side, no? Or we can also do this side, but let's just do this side. So if we create a line like so, this is 480, and this is 290 minus 230, which is 60. Then our radius should be just the square root of 480 squared plus 60 squared. Okay, so we need the radius so that we can compute for the principal stresses now. So if we have 480 squared plus 60 squared, then we have a value equal to around 483.7. Okay, so if we want to get the principal stresses, then we just by doing more circle, no? And let me zoom out, something like that, and something like that. Okay, so this is the sigma 2, and this is sigma 1, or we can call this as sigma max, no? And this is sigma min. So we have If you want to get this value, then we just add the center point. Sigma max is just equal to the center point, which is in this case 290 plus our radius, which is 483.7. I think you can compute that on your own, no? Then we have sigma min is just equal to 290 minus our radius, which is 483.7. Okay, again, you can compute this on your own, no? And with that, we've computed sigma 1 and sigma 2. And again, the convention is the lower the subscript, the higher the value. So if we have sigma 1, this is actually sigma max for a 2D stress state. And sigma 2, this is our sigma minimum. Okay. Now we need to find the orientation of the stress state, no? So this is saying how much are we rotating the axis to get the principal stresses, no? So we can compute it by taking the angle here. If this is theta, then for every 2 degrees in our Mohr circle, we are actually moving only 1 degree in the actual stress block, no? Or stress box. Okay, so we just need to compute this angle, no? So to compute this angle, we just do something like tan inverse of y over x, that's 480 over 60. That's roughly 82.9 degrees. And if it's 82.9 degrees, then we just divide it by 2. And you can solve this on your own, no? This is the amount of rotation we need to do to reach the principal stress, no? And if we look at it, this is moving in a counterclockwise direction. So that's 82.9 counterclockwise direction. Now let's do maximum shear stress. The maximum shear stress is just this value, no? So if you look at the Mohr circle, the maximum shear stress is this value or this value, okay? And this corresponds to, if this is your center, this actually corresponds to the radius. So the computed radius 483.7, this value here is also equal to tau max. Okay, so we computed that. Next is, let's say we rotated the stress state 30 degrees clockwise from the x-plane. What will be the resulting stress state? So what we'll do is, since we are moving it 30 degrees, we are moving the stress state 30 degrees. So in Mohr circle, we double that value, no? So we are trying to move this 60 degrees. Okay. And by moving it 60 degrees, we are trying to find what the stress states are. So if we extend that, so we are actually looking for, and let me use a different color now. So we're moving it 60 degrees. So we're actually looking for this point, no? This point, and also this point. Okay. So there are many ways to solve for these 2 points now, but perhaps the easiest and the most intuitive, graphically speaking, now is if we were to find this particular angle right here. Okay, so I'll just say alpha now. So if we find this angle alpha, and we already know the radius, no? So if we find alpha, then we can just use sine alpha and cosine alpha to find this value and this value. Okay, so we just need to find this alpha value over here. Okay, so we already know theta here, which is, our theta is 82.9, and the more accurate in textbooks actually use theta prime now to signify that it is the angle that is drawn in the Mohr circle. So if our theta prime is 82.9, if this is 82.9, and this is 82.9, and we have 60 degrees here, and this is a straight line, so it should total 180 degrees. Then our alpha should be equal to 180 minus 60 minus 82.9. Okay. And if you can manage to find alpha, then our x value here should be equal to just the radius multiplied by cosine alpha, while the y value is the radius multiplied by cosine, sorry, by sine alpha rather. So what do these two values indicate? This this x and y values. Well, since x is um, along the sigma axis, then it relates to the normal stresses, while the y value is a shear stress value. Okay, so here this point should actually be the center point plus whatever x you computed here now, and the tau value, since it's from the axis, then it's just 0 plus y, so it gives us y. Okay, so whatever value you compute here, you have now found the rotated axis now. Okay, and obviously you can find this on your own. No? This becomes c minus x and the same y value, but this time it's negative. So c negative y. So we're done with sample problem number 2, and I hope you managed to get the final answers, no, given this guy. Okay, so this is practice problem number 3, and we can solve the principal stresses of this particular stress block, no, using the cubic equation shown in module 3, where we are to solve the different invariants, no, the invariants I1, I2, and I3. But I'll show you a different method, no? And I think this is an easier method if you have a powerful calculator that can do matrix calculations. Okay, so before we begin, no, let me just show you that our stress tensor, and let's just call it as the matrix A. So this stress tensor is sometimes referred to as the Cauchy stress tensor. No? So we have the Cauchy stress tensor can actually be broken down into two components. Okay, so the first component is your hydrostatic stress. No, so the hydrostatic stress is just a stress wherein one normal stress is applied equally on all three directions. Okay, so for this case, let's just call that stress value as lambda, and I'll show you later why I chose the symbol lambda. So it should look something like this. So there are no shear stresses, and there is only the lambda value present in all three normal directions. No? Okay. So if this is the first component, then our second component should look like this, and this is again called the hydrostatic stress. No. Our second component, if if we were taking out lambda on each of the diagonals, then the second component should look something like sigma x minus lambda and sigma y minus lambda and sigma z minus lambda. Makes sense, no? Because if you add these two matrices, if you remember your linear algebra, if you add these two matrices, you just add each value in the same position. No? So lambda cancels out for each of the diagonal values, no? Which gives you the original stress tensor. Okay, and obviously you need to fill this out. No? So I won't write the subscript, but I think you already get this. No? Okay, so you have something that looks like this. And this is what we call as the deviatoric stress tensor. Okay. So from the deviatoric stress tensor, using what we call as an eigenvalue calculation, no? If we get and let's label this deviatoric stress tensor as as S, no, as the S matrix. If you equate the determinant of the stress matrix of the deviatory stress matrix, if you equate it to zero, then you actually end up with the different invariants, no? Because it results to what we call as a characteristic equation, no? And the characteristic equation uh, gives you the cubic equation, which involves the different invariants, no? So that is where that final equation comes from this particular I don't know, statement right here. Okay, so if we have a powerful calculator that can do matrix calculations, then we can actually just skip this step. No, we can evaluate from this point. Okay, and MS Mathematics 4, and I'll show you MS Math 4 in this video, no, how it works. MS Math 4 can actually compute for, can actually do matrix calculations. Okay, so let's use that so that we can solve for the different principal stresses, no. So in this particular case, when we do eigenvalue calculation, we actually solve for lambda, no. So lambda is that's why I chose lambda now, because lambda here is what we call as the eigenvalue. And for stress tensors, the eigenvalue is actually your principal stresses. So this is your sigma p, the principal stresses. And if you compute for what we call as the eigenvector, then you are actually computing the directional cosine, the directional cosines for the principal stresses that you are computing. Okay, so let's. I hope that makes some sense, no? And let's proceed with the MS Math 4 so that we can actually look at how we can evaluate this matrix. How can we can solve the eigenvalue of this matrix A. Okay, so this is MS Math 4, no? This is what it looks like. And let's try to compute for the eigenvalue of the stress tensor that we are given. Okay, so in the left corner, you have what something that looks like this, no? The linear algebra section. And let's first insert a matrix, no? So we are inserting a 3 by 3 matrix. Okay, and our 3 by 3 matrix, our Cauchy stress tensor was, we had in the x direction, we had 75 tensile stress. In the y direction, we had positive 200, so it's a tensile stress again. In the z direction, it was a compressive stress of negative 125, so it's compressive, so it's negative. Then in the x direction, in the x plane, moving in the positive y direction, we have 15 MPa. That's 15 and 15. Y plane, moving in the z direction, is 10. So it's positive y plane moving in the positive direction. Then lastly, we have in the z plane, positive z plane moving in the positive x direction is 25 MPa. Okay, so this is also 25, and this is. So we have our matrix. Now, if you remember, and let me just go back to our, our file. We want to get the eigenvalue, or to get the eigenvalue, we just need to equate the determinant of the deviatoric stress tensor to 0. Okay, and the deviatoric stress tensor is the Cauchy stress tensor with the subtracted lambda in the diagonal direction. Okay, so let's go back to our MS Math 4, no? Okay, so we have this one, so therefore we need to subtract a value, and let's just say an x value, no? So we use the variable x here. So this one, and we want to determine the determinant of this matrix. Okay, so the determinant of this matrix, so I can use this one. So the determinant of this matrix should be equal to 0. Okay. So I've set up the equation where we can get the eigenvalues. And if I solve this, if I press enter, I should get something that looks like this. So it automatically converts it. No? So you need to type solve. This syntax here is we are solving for the equation determinant of matrix S is equal to 0, and we are solving for the value. The comma here, comma separates the value you are trying to solve for. So this is read as solving the x variable in this equation. Okay, so as you can see, we have three solutions that corresponds to the three eigenvalues, and again, the eigenvalues correspond to the principal stresses. So here are the three principal stresses. So if you use MS Math 4, no, it's very easy to calculate. With just one equation, we just press enter, and it gave us the three principal stress values. No, okay. So with this now, if you did the I1, I2, I3 or invariance method, no, using the cubic equation with the invariance, try to compare our values, no, if hopefully we got the same uh, results. So I think I can leave the this final problem for to you guys. I'll give you a tip now. You can actually use mathematics 4 to solve for systems of equation. No? So the relevant syntax is nsolve, and you enclose it in a curly bracket, and you type your first equation here. So you have equation number 1, then you have equation number 2, and so on and so on. Then you close it with another curly bracket. Then you place a comma. Then you open another curly bracket, and this is the variables that you wish to find. So if you place, for example, in our case, for the directional cosines, we'll be using K, L, and M, no? So you can do K, L, and M, and you can close it in a close parenthesis, no? So, and take note that the number of equations you place here should be equal to the number of variables you are trying to solve for. Okay, so if you look at your modules, you actually have 4 equations. No, you need to choose only 3, and I'll leave that to you as an experiment of which equations you need to choose. So there is actually a right answer to this. No, and if you chose the correct equations, you'll actually end up with 2 solutions. So you'll have solution 1 and solution 2, but the 2 solutions will be just the negative of each other. No? So if you have, say, for example, you computed KL and M equal to, let's just assume it's -1, and let's just say something like that, no? So that those are just random numbers. Then solution 2 will just look like this. Okay. +1 and -1. So it's just the opposite sign solution. No? So the way you choose between these two solution is, di ba, we inputted, we can only input 3 equations here. So the last equation that we did not input will be used to determine which of these equations are correct. Okay. So again, you need to input 3 equations here, and the remaining 1 equation, you'll use it to determine which of this is correct. Okay, so try to do this on your own class, and I hope you'll find the MS Mathematics 4 useful. And with that, I think I can end the video. And again, thank you for watching this. I'll see you on Thursday.